In video 2 of module 5, we're going to be studying the Buckingham Pi theorem and seeing how we can go from dimensional variables to smaller dimensionless groups. And in the previous video, we had shown that, for example, one of these examples that CF, or the coefficient of force, was equal to a function of Reynolds. This is a way of simplifying an equation that said that force was equal to another function of length, velocity, density, and viscosity. And so the idea here is to come up with a technique in which we can find an equivalent between a coefficient of force and our Reynolds number. So we're going to do a general sort of idea of how we do this problem, and then we'll go into how to solve this problem with an example. So initially, I want to copy over a diagram, sorry, a sentence that describes what is happening. So we say our rule for our Buckingham Pi theorem is we're going to say that if a physical process satisfies the PDH, so PDH is the principle of dimensional homogeneity, and we had looked at this in the first module. That means that if it is a math equation and all the units are dimensionally homogeneous, then we have a correct equation. So this is a definition of PDH. And involves n-dimensional variables. So we have n is equal to the number of dimensional variables. And if we look at our equation above, we would have an example. So if we look at this equation here, we have an example that n would be equal to 5, right? We have force as a variable, we have length, velocity, density, and mu as well. So we can say that n is equal to 5 in this specific case. And we're then told it can be reduced to a relation between k-dimensionless variables or pi's. Okay, so that's an uppercase pi. So this term here is an uppercase pi, and it's the meaning of pi is essentially a number of dimensionless, it's a dimensionless variable that we're going to determine. And we can also call this k is the number of dimensionless variables we're going to have. Okay, and for now it doesn't really make sense, but it'll make sense in a second. So the reduction, okay, so J is equal to a reduction, is said to equal the maximum number of variables that do not form a pi amongst themselves and is less than or equal to the number of dimensions describing the variables. So pretty complicated explanation, but what I want to focus on is really this second part, because this second part is going to be true most of the time. So J is called the reduction, and we can say that it's always less than or equal to, and we're going to focus on this equal to. Okay, so we're going to say that in most cases, J is equal to the number of dimensions describing the variables. And we're going to focus on this definition as a rule of thumb because there are very few exceptions to this type of problem. Okay, we're not really going to see any drastic exceptions to this, and especially when we are working with the Buckingham pi theorem. Okay, the exception has to do with the fact that it equals a number of variables that do not form a pi amongst themselves. But we'll talk about what that means and when this term is, for example, less than the number of dimensions describing the variables. So J is essentially how many dimensions are we using to describe all our variables. So if we have a certain number of dimensions, we know that we can choose between mass, length, time, and pi. So if there's only 3 dimensions out of the 4, J would be equal to 3. If there's only 2 dimensions out of the 4, J would be equal to 2. So for example, in our system where we have force is equal to a function of length, velocity, density, and mu, you would have mass, length, and temperature. We do not, and time. We do not have any theta term, which is relative to temperature. So we can say that in this case, in our case of our previous example, we can say J is equal to 3. And J is usually equal to 3, and J is usually equal to that number of dimensions used in our dimensionless parameter. In some cases where there are problems, you might not be able to use J equals 3, in which case you would use J is equal to 2 or J is equal to 1, depending on the problem. But in most cases, you can take this as a rule of thumb. And if there isn't, you would probably be told to try a different J on purpose. And from our problem, it says that the reduction is equal to n minus k. So we know that J is equal to n minus k. So essentially the reduction is equal to n, which is the number of dimensional parameters, which is 5, minus k, the number of dimensionless parameters. So in this case, if we know that, for example, J is equal to 3, n is equal to 5, we can say that k is equal to 2. So we would have a term called pi 1 and a term called pi 2. And these terms, pi 1 and pi 2, would replace CF and Reynolds, okay, in that specific example that we were talking about, okay? So the idea is to follow a procedure, and we're going to see how we can follow a procedure and essentially figure out how we can solve to find what our CF would be equal to and what our Reynolds would be equal to. So I'm going to copy over a step-by-step solution of what we should do in these types of problems, and we're going to discuss it, and then we're going to do an example problem using that step-by-step procedure. So let me copy over that step-by-step procedure. And we'll discuss it once it's copied. Okay, so we're told the first thing we should do in any problem, given an equation as a function of another one, we say to list and count the n variables involved in the problem. If any important variables are missing, dimensional analysis will fail. So that will be in the case of our previous example. For example, just to show you, we would have force is equal to a function of velocity, length, density, and mu. We said that n is equal to 5. That's our first step. Okay, so step 1. Step 2, we're told to list the dimensions of each variable according to MLT theta or FLT theta. So most of the time we're going to be using the MLT theta system. And conveniently for you, a list of all the dimensions of each parameter is given in table 5.1 in your textbook. So you're invited to use table 5.1 in your textbook if you want to use the dimensions from there. Now, for example, as an example, the dimension for length would be length. The dimension for velocity would be length per time. So it would be LT to the minus 1 for velocity, and so on. And we're going to do an example of exactly the same parameters soon so that we have an idea of how we actually derive our values for CF and for Reynolds. So we're actually going to do an actual example. Okay, then step 3 says find J and initially guess J equal to the number of different dimensions present. And for now, we're going to really leave it at this. We're going to guess J equal to the amount of dimensions present. So if there are 3 dimensions, J would be equal to 3. And these dimensions come from this term right here. Okay, if there are 2 dimensions, J is equal to 2. And then we would look for J variables that do not form a pi product. And we're going to look at what that means when we get to our example problem so we can really explain what forming a pi product means. Then if that doesn't work, you would reduce it by 1 and look again. And with practice, you're going to be able to find J very rapidly. It'll make it very easy to solve. And you can look at your examples in your book. We're going to be doing example 5.2 right after this description, but the other examples in your book explain very well how to use the Buckingham pi theorem. So next, it says select J scaling parameters that do not form a pi product. Make sure they please you and have some generality if possible, because they will then appear in every one of your pi groups. So usually you want to pick density or velocity or length. So in step 4, what we're trying to do is, we know that J, for example, in our previous example is equal to 3 because we're using MLT. Now we have to pick which terms will determine J. So which terms are going to be J? So usually you want to pick density, velocity, or length for your J. You want to keep things as simple as possible. And you also don't want, if you have 3 parameters, so M, L, and T, you do not want to have a term with all 3 terms in it. You want to try and have independent terms. So for example, if you pick length, you would have L. If you pick velocity, you would have LT to the minus 1. If you pick density, you would have M L to the minus 3. So mass per volume. And you can see that all 3 are independent of each other. They're different from each other. And they also don't use all 3 terms at once. You do not want your J to have all 3 terms at once. And it'll become clear once we do an example problem, but these are just the rules for now. Okay, it says do not pick surface tension, for example, or you will form 6 different independent Weber number parameters and thoroughly annoy your colleagues. That's some extra information that you don't really need to know at this point, but it's just extra information that your book gives you as sort of a guidance if you're looking for the Weber number, which is another number that we're not really going to talk about too much. Okay, then it says, as step 5, add one additional variable to your J repeating variables and form a power product. Algebraically find the exponents to make the product dimensionless. Try to arrange for your output or dependent variables, force, pressure drop, torque, power, to appear in the numerator, and your plots will look better. Do this sequentially, adding one variable each time, and you will find n minus j is equal to k desired pi product. Okay, so essentially, once we have our 3 parameters, our next step is to, in this long phrase, what we're trying to do in step 5 is just to set up our equations for pi. And we're going to talk about how we're going to set up our pi equations. So we know that our equation to find pi is, to find the number of pi's that we have in our system, is k is equal to n minus j. So we know that in our case, for example, we have 5 minus 3, which is equal to 2. So we have pi 1 and pi 2. And this pi 1 and pi 2, we're going to figure out how to do through the example problem. Now, it tells us in the statement to add one variable to your j repeating parameters. So we can add one of the 2 variables to our repeating parameters. So we have 2 variables left out of density, velocity, length we already used. So we can either add force or mu. And once we add force or mu, we're going to see how we can solve this problem. Okay, but for now, we're just going to keep it like this, and we're going to do it through the example. It'll be easier to follow. Okay, and then part 6 is write the final dimensionless function and check the terms to make sure all pi groups are dimensionless. So you want to make sure that all pi groups are going to be dimensionless. Okay, so now let's use this instruction sheet and instruction list to do an example problem explaining what is happening and making sure that we understand what is happening overall. Okay, so let's look at the example problem in itself. So the example problem that we're going to do is example 5.2. And I'm not going to write the example down because it's very, very simple, but we are told in example 5.2, we are told to find CF is equal to G of Reynolds from force is equal to a function of length, velocity, density, and mu viscosity. Okay, so we're supposed to find a dimensionless relationship between CF and Reynolds from our force is equal to a function of length, velocity, density, and viscosity. Okay, and we're gonna follow the steps. So the first thing we're gonna do is count the variables. We know we have, in this equation, we have 5 variables. So we can say that n is equal to 5. The second step says, step 2 says to list all the variables in terms of dimensions. So we're going to list force, length, velocity, density, and mu as a function of their basic units. So force is equal to mass times length times time to the minus 2. Okay, or mass times length divided by time squared. Okay, it's essentially mass times acceleration. Length is just L, velocity is LT to the minus 1, density is M times L to the minus 3, and viscosity is also given in table 5.1 is ML to the minus 1 T minus 1. So you can use table 5.1 for this. Okay, you don't have to remember all of these, but you can use table 5.1 in your textbook. Okay, moving forward from this, in step 3, we're told to find J. So we know that we have a possibility of using MLT and theta. We have no theta. Therefore, we're going to assume j is equal to 3. Okay, and from j is equal to 3, we know from our end, n, that k is therefore equal to 5 minus 3, which is equal to 2, and therefore we have 2 pi terms that are going to be used in our equation. Okay, and we're going to assume j is equal to 3 except if something doesn't work. Okay, the reason we can choose j is equal to 3 is because if we go to step 4, in step 4 we're going to choose repeating variables. So we're going to choose the repeating variables, which are our j. So what we're doing here is we're going to choose the repeating variables that are going to go in our equation. Pi 1 is equal to a function of pi 2. So what we're doing essentially is to find the variables that are going to go in here and are going to be repeated. And the terms that you want to use for the repeating variables j are the variables that do not have all the terms in the dimension. So you want to use the variables that do not have all the dimensions in one. Okay, so the 3 that we could use from our system are this one, and this one. They're the only 3 in our equation that don't have all 3 terms. For force and mu, we have mass, length, and time. And for force, we also have mass, length, and time. So those 2 would not work as repeating variables. So we're going to choose repeating variables that are independent of each other and have different measures of dimensions. Now we can also say that if we put them all together, if we multiply them together, so if we multiply LV and rho in some way or another, we know that they have all the dimensions. So that's another good step in the right direction. We want to be able to have all the dimensions from our 3 repeating variables. Okay, so then we've chosen our 3 repeating variables through our rule of using the variables that are the simplest and that don't have all 3 terms at once. And now we can write in step 5, we're actually going to solve for our pi. So how are we going to do this? Well, we're going to do it in the following way. We know that our pi's, pi 1 and pi 2, are dimensionless. And what dimensionless means is that pi 1 is going to be equal to mass to the power of 0, length to the power of 0, and time to the power of 0. If we have something that's dimensionless, the mass, length, and time term should all be to the power of 0. Okay, we know that for sure because we're told that they're dimensionless. Okay, same thing for pi 2. Pi 2 is also going to be equal to m0, l0, t0. And now what we're going to do is we're going to say, we're going to use, for pi 1, we're going to make it a dimensionless parameter of force. And pi 2, we're going to make it a dimensionless parameter of viscosity. We're going to choose our two remaining variables to be used. And what we're going to do is we're going to combine our repeating variables which are length, velocity, and density with these terms on the left. So you can set up your equation for pi 1 and pi 2 to say that pi 1, okay, uppercase pi 1 is equal to m0, L0, T0, and is going to be equal to force times length to the power of A times velocity to the power of B times density to the power of C. And now we're going to try and make our basic units all go to 0. Okay, so for pi 1, we're going to have the following equation. For pi 2, just to write the equation down here, and then we'll solve them one by one, we can say that pi 2 is equal to m0, L0, T0, and that would be equal to mu, the viscosity, times length to the power of A, times velocity to the power of B, times density to the power of C. And now we're just going to equate the exponents to try and make sense of the equation. So what we can do is we can take this equation and try and solve for it. So for pi 1, we're going to equate the exponents. And before we equate the exponents, let's write our pi 1 all in terms of m, L, and t, as opposed to in the form force, length, velocity, and density. So we have that pi 1 is actually equal to m0, L0 times T0, and this is equal to force, which our term for force is m, L, T to the minus 2, times L to the power of A, times L, T to the minus 1, all to the power of B, and m, L to the minus 3, all to the power of C. So when you have something all to the power of, you have to make the power of both systems, okay? So now we can equate all the exponents with 0, essentially. We can sum all of the exponents because everything is multiplied by each other. So if we equate the exponents for length, we have that 0 is equal to 1. So we have 1 from this term right here. Then we have A from this term, B from this term, and minus 3C from this term. So we're going to write 1 plus A from the second term plus B from the third term minus 3C is equal to 0. And for mass, we can do the same solving where we have 0 is equal to now the mass. So we have mass to the power of 1. So we have 1 plus we have mass repeating in C. So plus C. And finally, for time, we can say that we have minus 2 from the first term minus B is equal to 0. Okay, so now we have 3 equations and 3 unknowns. So we can say that B is equal to -2, C is equal to -1, and A is equal to -2. And so we can say that our pi1 term, if it is dimensionless, our pi1 term will be equal to, we just plug in the values for A, B, and C, and we should get the right answer. So it's going to be equal to L to the -2, simplified, times V to the -2, times density to the -1. So I've already skipped a step and simplified and equated all our M, L, and T's back to our density term, our velocity term, and our length term multiplied by F. So we just go back to our simple term for pi1, which was FLV times density or rho. So we have that the length was to the -2, the velocity was to the -2, and the density was to the -1 in order to get a dimensionless parameter. So we can say that pi1 is equal to F over density times velocity squared times the length squared, and this is our equivalent to what CF should be. If we do our pi2 in the same way, our pi2 can be said to be equal to m to the power of 0, L to the power of 0, T to the power of 0 is equal to mu times L to the power of A, V to the power of B, and density to the power of C. Those are our three repeating parameters. We have that this is equal to m L to the -1, T to the -1, multiplied by L to the power of A, multiplied by LT to the -1 to the power of B, times ML to the -3 to the power of C. And if we equate all three equations, we finally get that A is equal to -1, B is equal to -1, and C is equal to -1. So I invite you to look at the solution to this example in your textbook if you want some extra clarification on how to equate our powers, but essentially you just make 0 equal to the powers on the right side. And we're left with a pi2. If everything is -1, okay, you just plug in -1 to all of this here, and you get that you have mu over density, velocity, and length. So I just divide for the power of -1 essentially. And so this is equal to actually something a little bit different. It's equal to 1 over Reynolds number. Okay, we had said earlier that in last video that Reynolds was equal to rho velocity times length over mu. And we actually here get a function that says CF is equal to force divided by density U squared L squared is equal to a function of mu over density times velocity, and this is velocity of V, rho velocity times L, and we see that this function is actually equal to 1 over Reynolds. So what we can do is, with a little bit of a different approach, we can say that if we have a function of mu over rho times V times L, we can say that we can use another function, we can name another function that would be called g of rho VL over mu. It's just the inverse function. So it's exactly the same thing, and then you have to figure out the function. So we can say that CF is equal to a function g of rho VL over mu, which is equal to G of Reynolds. And this G here has to be determined by experiments. This number is determined by experiments. Okay, that's very important. So essentially, you're making a graph of either CF to the 1 over Reynolds, which was our original function, but we can make another graph that's just CF versus Reynolds. And from the line that we have, we can find our function. Okay, pretty interesting. Okay, so this will conclude our second video on Module 5, and we'll be back in video 3 of Module 5 to discuss some more alternative methods of non-dimensionalizing basic equations.